I don't think I can make it full screen proper in this setup, but perhaps this will be okay. Let me clean up the screen a little bit, at least, so it's a little bit less distracting. Okay, and that's about as good as it's gonna get. Hello, my name is Federica Bianco. My pronouns are she, her. I'm from the University of, well, I am affiliated with the University of Delaware Department of Physics and Astronomy and Biden School of Public Policy and Administration. I have a fairly interdisciplinary portfolio of science and policy related work, but today I will focus, of course, on astrophysics and astrophysics at the intersection of with AI. And before I do anything else, I need to just give a shout out to my team. It's called FastLab, Federica's Astrostatistics Laboratory at the University of Delaware since 2019. We study the sky and more, mostly with AI. This is not a colloquium, so I will not show you all of the projects that my students and postdocs that are related and affiliated with FastLab in any ways are working on. I'll just possibly have a couple of highlights, but please keep in mind that they do the work and I just try to steer the ship. So I'm going to start with the fourth paradigm, which is a fairly old concept by Jim Gray. When the Slow and Digital Sky survey was emerging, and Microsoft was interested in the concept of the survey because it was providing this very rich, very interesting data set, which was also very safe to work on. And so a really good platform for AI. And this remains a recurrent theme of why we may want to do astronomy at the intersection of AI or AI at the intersection of astronomy. And so the idea is that science and the science inference have gone through different paradigms over time. More or less, I don't think you put dates on it, but I dare put in dates even. More or less, from minus infinity to 1900, we were doing science on an experiment-driven basis. We were trying to put, balls on planes at an angle to measure velocity of the balls and try to figure out what could that possibly mean? How can I derive some laws about it? What made those laws? In the 1900s, we started developing a concept that we could do science in a more theory-driven fashion. So this relates to the principle of falsifiability and the idea that if I have a hypothesis, a theory, that should principally, in order to be scientific, be a falsifiable theory. I need to be able to predict an experiment and the result. And if the result is not different than I predicted it, and I don't throw away my theory and I hold it as my best understanding of the universe that or the piece of the universe that I'm studying for now, which is a great concept because it also allows for a natural idea of why science progresses, why we have some laws of science that then get modified into different laws, because we have better data that can now invalidate the predictions that we had made earlier. In the 1950s, of course, we have the computing revolution, and so we start doing science in a computationally driven manner. That means we start integrating the idea of simulations, Monte Carlo methods in science, and that's another really significant paradigm shift. And then the one that really this leads up to what Jim was interested in. Now we're entering, and now back then was in the 1990s, an era of data-driven science. And astronomy is really at the forefront of this because we have established a really effective way to collect large amounts of data because our data is not only large, but typically highly dimensional, highly complex. So it's a very interesting data set for a data-driven science paradigm. And you may see these four paradigms in talks, for example, by other scholars like George Rodowsky, who started the Catalina SkAI survey, but from a talk by Alex Saleh, who was really involved in this process and a good friend of Jim Gray at the time. He started postulating we are now possibly in a new paradigm shift where we enter AI-driven science. And it's not obvious, perhaps, yet what that means and what is the difference between just being in a data-driven scenario and being in an AI-driven science scenario. And I'll try to tell you what I think it means. but I'll start with a little bit of history. I really like this clip, so I put it in all my classes and most of my talks when I get to talk about AI. So this is a clip from 1958. So we're at the true infancy of neural networks, like 2-3 years in. And all they have is this circuit board, effectively, that can do binary operations. But I really love that at the time, our hope in the progress that AI could lead to was such that this New York Times, no less, article says the Navy revealed the embryo of an electronic computer today. Sorry. Of an electronic computer today, that it expects it will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. The embryo, the Weather Bureau's $2 million 704 computer, learned to differentiate between left and right after 50 attempts in a Navy demonstration. So I love the leap of faith that if we have something that can tell left from right in 50 attempts, we are in the presence of something that can evolve to be conscious of itself. But we really are at the cusp of this discussion. Right now is when we really start with some reasonableness, thinking, are we really seeing the beginning of conscious AI, of general AI, et cetera, et cetera. Okay, I have an interactive portion of the talk. So this is a Slido. I trust you know what to do with this image. And if you don't want to do the QR code, you can go to slido.com and plug that number in. And there's a quick question for you. I'm going to give you a second to grab the QR code. The question for you is, when do you think was the first time that review articles on AI in astronomy appeared in the literature? What year? I don't see any phones up anymore, so I'm going to move to this, which hopefully will show us the results. Slido is always a little bit iffy. But, okay. So I'm doing a sociological experiment because I keep showing this to different audiences. I love the absolute chaos that this plot produces. We have some votes for 1970s and some votes for as late as 2015, which I think is interesting because it demonstrates that even AI savvy audience as as the people in this room, it's hard to keep track of what is actually how this intersection of sciences has evolved. Let's see. I'll reveal the answer. Please feel free to contribute. I'll keep all these data for my sociological research adventures. At some point, you will be co-authoring a paper. I think the earliest that I found were from the 1990s, early 1990s, which to me is mind-blowing, that we had review articles that early on, that we were already doing enough AI to be able to talk about collection of works and possible applications of AI to really interesting problems that are the same problem that we are talking about applications of AI in perspectives in some cases right now. In particular, there is a really interesting work on classification and optimal telescope scheduling. And classification of astronomical objects seem to be a very obvious outcome for AI and astrophysics. There was even a book. Last time I showed this slide, somebody pointed out that there's something even earlier. This is 1988. There was a book about this. Okay. So what do these early works we're focusing on is a little bit different than what we're doing now. So the topical problems were the same. And in particular, I'm really interested in this optimal classification, optimal scheduling of telescopes. I'll tell you why in a second. In reality, this paper doesn't really build a neural network. It builds a neural structure, but there's no training involved. So it's actually a deterministic model that uses the structure, like the topology of a neural network. All the other ones are actually neural network problems, and I'm going to flash a couple of other papers by pioneers. Galaxy recognition, again, 1988. The Story Lombardis had done a lot of pioneering work in applications of AI to astrophysics. And again, we see morphological classification of galaxies, a problem that we're working now on solving with neural networks. Spectral classification, same thing. But in terms of numbers, the publications were really limited until about 10 years ago, and then the field exploded. This is the number of papers that include machine learning, artificial ML, artificial intelligence, AI, deep learning, and neural network in the abstract. So we're at like thousands of papers every year. Okay. There's this really nice paper by Smith, and I don't know how to pronounce the name of this fellow, Gach, I'm not sure, from 2022, and I like this quote. In 1994, Ofer Lehigh had an early tribalizer, wow, that's hard to read, identified a neuroskeptic. Those resistance to the use of such techniques in serious astrophysics research, love the use of the word serious there, and argue that artificial neural networks should be viewed as a general statistical framework rather than an esoteric approach. Unfortunately, this skepticism has persisted, and despite the recent upsurge in the use of neural network, most of the criticism of machine learning technique and deep learning in particular is leveled at the perceived black box nature of the methodology. And this is really something that I really care, and I hope the SkAI Institute can really contribute to debunking, absolutely, because there's nothing, obviously, there's nothing ontologically mysterious about neural network. At the root, what we're all trying to do, what we've all been trying to do the entire time, was trying to figure out how we go from some input, which are observables, to some output, which are also observable. And what takes us there is the physics that we're trying to extract. And we approximate it with a function. So anytime that we do machine learning, we approximate that physics with a function that has parameters that we're going to learn from the data itself. So for example, that function can be sort of in the simplest case, a linear regression, mx plus b. I have two parameters, the slope and the intercept. How on earth am I going to select the parameters that fit my problem? I'm going to look at some data, and I'm going to choose the slope and the intercept on the basis of how good my predictions are with some concept of a loss function or objective function. And I think we did a disservice to the world and humanity by calling this learning, because really this is just optimizing parameters, and we anthropomorphize the process in such a way that might have led to some of the skepticism and some of the fear, perhaps, of the whole field. Okay, so obviously linear regression is at the heart of a lot of astrophysics. A lot of people have worked on this, fitting galaxies, galaxy velocity or supernovae-like curve to lines to find out whether the universe expands, how fast does it expand in an accelerator, or does it fashion, or does it slow down? And linear regression is something that we've done well before that in the first appearance of the concept of regression is from 1885 with this title of this paper, Regression to Mediocrity, which was actually about regression to the mean, but something to say about that. Okay, so of course that function f of x, which represents our physics, in most cases will not be a line, just because in most cases the line is too simple a problem, it's not that interesting. But as complex as we can make that function, the process doesn't change. And a neural network is really just a complex nonlinear operator that I interpone between my observables input and my observable outputs. Okay. Some machine learning methods are perhaps easier to digest. Here is one example. Tree methods, they're very powerful. Most of the, until a few years ago, if you look at most Kaggle challenges that had to do with physics, for example, high energy physics, there were a few, they were actually typically won by gradient boosted trees and not by neural networks. Until, I'm gonna say like maybe 7, 8 years ago. And obviously, there's an advantage in using something like a tree-based method, at least in terms of like psychological comfort of the user that can map that onto something that they can read, like a flowchart that is not unlike the one, that some people here probably had gone through when they decided whether they wanted to go to grad school. Do you like studying? Do you like never sleeping? Yes, no. And so there is the interpretability in principle is much more obvious, goes through much more obvious humanly reasonable paths. There's a whole lecture that I could give you on how this is absolutely not true, because once you put covariance into the problem, the interpretability gets out of the window. Let's not go there today. But so why can't we just stick with methods that are interpretable? I think there's one key feature that attracted scientists, data analysts to AI for solving astrophysical problems, which is that if I apply something like a tree method, I need to extract features from my astrophysical data before I can pass them to the model. So for galaxy classification, I would extract morphological features like, is it elliptical? How elliptical is it? Does it have spiral arms, et cetera, et cetera. But if I use a neural network, and I'm generally sort of thinking of AI as neural network in a very, very vanilla way at the moment, I can bypass that to some extent. I can just feed the raw feature to my neural network, and it's going to have a larger capacity and larger forgiveness to the way in which the features are passed. So I can, for example, pass it directly some images, as opposed to having to extract parameters of the objects in the images. And I think that's how a lot of what really started people working a lot with neural networks compared to other models. Okay. There's another thing, though. The fact that neural networks continue to be really, really promising. Back to our New York Times article from 1958. We can now quantify in some way the reason why we have such expectation for neural networks. So these are scaling laws of neural networks calculated by Google in 2020. And Google was thinking of setting up ChatGPT. And they had a very practical problem. Before I spend millions and millions of dollars on GPUs and on energy to train a model that is substantially, transformationally larger than anything that we trained before, I need to make sure that I have a reasonable hope that it will perform substantially better than anything that we trained before. So they started looking at scaling laws of performance. And so what you see here is a metric of performance, the validation loss, as a function of the number of computation that my neural network does. And while each one of those individual neural network flattens out in performance, so this is like you can think of this as your training loss curve, right? So it flattens out at some point, but as I increase the number of parameters, each one of these curves is a larger neural network, I reach a better solution. I keep continuing to minimize the loss. We don't fully understand it. There's a lot of research that is devoted to this. But the fact that this looks like a linear function in log space is really mysterious. Sorry, there is an E missing from my compute optimal frontier, which is what we call that boundary, and really intriguing, because at the moment, we don't know that at any point neural networks may stop improving so long as we have more GPUs and more mile islands to build nuclear power on, so that we can power these things. And also, similar scaling laws, similarly mysterious, are seen with the model size, with the data set size, and in fact, like the details of the model, to some extent, like the details of the architecture are a bit of a wash compared to these fundamental quantities. There's a lot of research, like I was saying. I think maybe this paper is arguing that we may be seeing why the behavior is what it is, but I'm not qualified to talk about it. And many people in the room are, so I don't dare. So So neural network is basically just a function that maps input to output, but it does it potentially extremely accurately. And also, in the process of doing it, it generates an internal representation of the data that can be really, really interesting. And a lot of astrophysics research and research in AI in general is moving towards like, let's understand the latent space, not only for interpretability. We will, of course, have a lot of research in interpretability, but also because the latent space itself, the way in which it organizes itself, may be interesting, may teach us something about the data. Okay, where am I going from here? Right. Do we have an opportunity? Of course, at the same time, there's this big opportunity for astronomy. And the reason why you started seeing a lot of development of AI in astrophysics in 2014, also, I'm going to argue, has to do with Vera C. Rubin Observatory. So this is my little spiel about the Vera C. Rubin Observatory, which we're building in Cerro Pachón, Chile. It's a joint project of the US National Science Foundation and Department of Energy. It's got 4 scientific goals, primarily to probe dark energy and dark matter, to build an unprecedented catalog of solar system objects, to map the Milky Way and local volume, to explore the transient and variable universe. But in addition to these goals, and these goals were specifically designed to be different from each other enough that if you try to maximize your observing capabilities, your observatory, for all these goals at the same time, you stand a good chance of really also transforming the space in between. So something that you don't see here, but we do fully expect Rubin to be transformational in its low surface brightness science, galaxy science. They're not here, but they live in the space in between these places. I'm not going to go over the details of the surveys, just a lot of everything. Possibly the most a lot of everything is the camera. That's a lot of pixels, 32 gigapixels, largest declassified camera ever built. But it's the DOE LSST camera, and it was, yes, my mandatory pit stop at the Sphere. The Sphere in Las Vegas, you may know this, is a facility in Las Vegas. You two were in residence. That's kind of the caliber of facility that it is. And their motto is built as the world's largest video screen. The giant ball can display anything. I'm here to tell you that that's a bunch of baloney because it can only display about 1/17 of an LSST image. And the LSST images are flowing. As of April 17th, the camera has seen photons. This is our team looking live at the first image that the camera took. And in June, we were able to release these images, some of these images to the public. I had a whole 1-hour interview with this great journalist, Davide Castelvecchi, on Zoom. Maybe it was even an hour and a half. I was late for my next meeting. And then I was so waiting and so excited to see what he was going to write about all the things that I said. And the article opens with, "There are so many stars." This may sound like an obvious thing for a professional stargazer to say, but astrophysics Federica Bianco is reacting to something extraordinary. And this is one of the images. This is not a single image. It's a stack of 678 separate images of the Trifid Nebula. I want to show you a few data products because I'm really excited about this. This is pretty, right? It's really waiting to be put on a scarf. This is the Treasure Cove. It's the Virgo cluster. This is when I said there are so many stars. There are really so many stars. I want to show you something cute, and I hate that I just will use the word cute, something awesome that we did with these images. We sonified, and to my knowledge, we are the first project that had a sonification of the data at first look. Many projects have sonifications of their data, of course, but we really pushed to have one right as we started the survey and right as we presented the first images. So I'm going to give you about 10 seconds of this. Hopefully it works. I don't have a lot of volume. I don't have a lot of volume, so I'm going to stop it, but I encourage you to go hear it. I was going to say, look at it. I'm encouraging you to go hear it at the skiviewer.app, which is our app for presenting the LSST first look images. Let me skip over the asteroids. There's a ton of asteroids. There's a ton of transients in the data. And we're now releasing the data for scientific purposes. DP1 is the first data release. It actually is ComCam data, so it's a smaller camera, but it's one chip of the camera. It was our initial commissioning, and we'll release the commissioning data from LSST-CAM as data preview 2 or DP2. So that's all cool and exciting. Will we get more data with LSST? Hell yeah. LSST is roughly an order of magnitude in any dimension that you can think of over the other surveys. So it's about an order of magnitude more data than precursor surveys. But we're already in the era of big data in astronomy. But I do think that having LSST at the horizon for the past like 10 years, 10 years has really pushed both AI to solve the problem of big data and also other surveys to really collect large amounts of complex data to help us prepare for LSST. I've got a bunch of numbers here. There will be 17 billion stars, 10 million quasars. We roughly have 10, it's roughly a factor 10 over what we have right now. 50,000 tidal disruption events we expect. We right now have 150. 10,000 superluminous supernovae from the roughly 200 that we have now. I'm going to keep going and just flash more numbers. 10 interstellar objects from 2. We already had one. We already saw one. It was in the data. And of course, true novelties. Who knows what they will be, right? So obviously, this motivates shifting gear and moving on massively to AI for analyzing these data. How much time? When do I finish?
Technically 2:30, but you started slightly late, so.
Okay. But as Yang Huang from the University of Chinese Academies of Science said, at the University AI workshop in Greece, also Vicky was this summer, big data does not mean big science. So LSST will provide the data. How do we do the science? Hopefully with AI. Who does the science? All of us, because the LSST data has no proprietary restrictions in the US and Chile. Okay, I'm going to go now sort of ping pong across a few topics that I think are interesting from the perspective of developing developing AI solutions to astrophysical problems. It's going to be a bit scattered. It's by all means not going to be exhaustive, and it's going to be very biased towards the transient and variable universe, because that's what I study. I think I have a slide in there to say like there's also a lot of stuff in the static SkAI. I see a lot of people here that work on that, but that's not my daily bread, so I'm not gonna talk about that much. The first one is the one that I think is farthest away from AI solutions in general, and it's survey optimization. So let me give you a sense of what it means, but it's very close to my heart because that's leading the committee that does the survey optimization for LSST is one of my responsibility as deputy project scientist. And we're going to take 800 images of every position in the sky over 18,000 and plus square degrees. So that is a lot of images. In which sequence do we take them can really make or break the science that we do with LSST. If we take them evenly spaced in time, the interval between images is large. Then we cannot do rapid evolving transients. If we take them in a compact way, then we cannot survey things over long periods of time. We lose the long-lasting transients, and we may have inhomogeneity in the survey that may not be appealing to our static SkAI colleagues. So there's more than that too, because LSST is just one, as big as a piece of a puzzle it is, it's just one piece of the puzzle in discovery, in astrophysical discovery. LSST works as a discovery engine. We map the sky repeatedly, so we see things that change, and we measure how they evolve, we discover new things. But then those things need to be followed up, because LSST is only a photometric instrument. We only take images, for example. We don't take spectra. We may not take enough data of a given object, or we may not take it in the right wavelengths. So software that follows LSST distributes these alerts about all the things that we find that change in the sky overnight. And by the way, that's 10 million alerts that we expect every night to the world by collecting them from LSST and also aggregating, classifying them, pre-processing them, combining them with information from other surveys. There are automated systems that can deploy observations at telescope where people have time to follow up the discoveries. And then we would like the data that gets collected, whether it's at different wavelengths or by different telescope, to go back into the loop. Somewhere there isn't, yeah, there. To go back into the loop and be fed into the brokers and into our overall knowledge of these objects. This is a very complex process. So a shout out to Adam Miller, who published this year, and Nabil Rahmullah, I probably butchered your name if you're in the room, who published this past, well, 2 years ago now, 2023, the first fully robotic discovery. So ZTF took the observations were processed, an alert was initiated, meaning that something that changed was detected, and that automatically triggered the spectroscopic follow-up with the SED machine and the automatic classification and the automatic publication of a circular notifying the discovery. This happened, Adam tells me, entirely during the night hours when nobody had to stay awake to babysit the process. And this is really transformative. But there is more, because the survey of Rubin LSST is alive and is designed to continue evolving and be changed, partly because we expect LSST to be transformational in discovery. And so we want to be able to change the survey strategy to changing scientific needs. And right now we do that by asking the community, how well are we doing if we implement this on your science case? And they give us a number, and we optimize over those numbers. And we have a committee of about 15 people that does this optimization. And we do it in a repetitive process over and over again. We've done it like over 10 years, and we have substantially changed the footprint and the observing strategy altogether. But in operations, this will be a much more significant problem, because in operations, this will not be just a hypothetical survey strategy that I can propagate over 10 years, but things will happen, and we need to be adjusting to what is actually the reality of observations. I'm gonna work myself out of my own job by telling you that I think we need to seriously think how to deploy an AI to do this process instead of having me chairing a committee of people. And I actually think that the main problem here is not going to be technical, it's going to be sociological. It's going to be having the community accepting that an AI can solve this problem in a way that is just as good as people reasoning in a room. Okay. Now that I no longer have a job in Rubin, let me tell you about other things. I'm realizing that I'm running out of time, so let me talk about this first. So I think, yeah, let me start here. So one of the things that Rubin will do, 10 million alerts every night for 10 years. That's ridiculous, right? What is an alert? It's something that I see when I compare two images of the same portion of the sky that has changed. Details, it's a lot more sophisticated than that, but to zeroth order. So normally when I see something changing, what I want to do is start staring at it and use two telescopes at least, one to get a light curve, which is what astronomers call a time series of brightness of an object, and also a spectrum, or ideally a series of spectra that follow the change in the emission across wavelengths over time. That really tells me about the physics. So the light curve is like a compressed version of the spectrum in a limited range. But the spectrum really tells me what are the chemical elements that are in the object, what is the temperature of the object, and really are the fingerprint of the physics. The problem is that there's not nearly enough, and when I say nearly, I really mean nearly enough glass in the world pointing at the sky to collect spectra for even a small fraction of 10 million objects per night, and remind you that I said I want a time series of all this. So this has really put a lot of stress on the time domain community, because we know that the way in which we normally do science, which is to look at a spectrum to decide what something is just not going to work for the most part, because for the most part, we will not have spectra. And Alex Galliano, when he was a grad student, hi, Alex, I show this slide in most of my talks, has made this beautiful visualization to show the magnitude of the problem. So this is the number of spectra of discoveries over time, starting back in the 1900s, and the number of discoveries that are associated with a spectrum. And you can see that the number of discoveries that are associated with spectra is already dropping. It will be ridiculously low in LSST as a fraction of the total number of discoveries. So we need to work with likers, but likers have a problem, I think, for AI, and there's a problem with data encoding. So if you study galaxies, and again, shout outs to a lot of awesome AI and static SkAI solutions and projects that I'm not talking about, flash. But so if you're used to doing not time domain astronomy, well, normally you think of things like this, and you want to apply AI to something like this. This visualization was conceived and created by Alex Razin, so shout out to her. This is what we work on as time domain astronomers. So good luck, because that's your data. And that's really tragic. And we really lose so much information because our sampling is sparse, both in wavelengths. When we apply the likers, Rubin has 6 filters. We have multiple likers that covers only a limited range of wavelengths, and in an unevenly sampled and sparse way. And of course, in time. And uneven sampling is really critical in time. If I had an ideal light curve, it would look maybe something like this. ZTF light curves look something like this, only 2 bands, slightly denser sampling than Rubin. Rubin light curves look like this for 7% of the data. Those are the deep drilling fields. But the majority of them look like this. So now this is our daily bread for us time domain astronomers that think of Rubin. This is what we want to apply AI to. And that's a massive problem, because this data is extremely information-starved compared to the objects that we want to study. Nonetheless, there have been great results on photometric classification, for example, of transients. This was a very successful Kaggle challenge initiated by the Rubin community, the Science Collaboration Desk, TDS, etc. So the challenge is to classify light curves. So this is a nice binary eclipsing light curve, but classify them when they are LSST-like light curves. So that's a similar object in the LSST data set. And surprisingly, we had great success at doing that. But let me emphasize, why are light curve really bad tensors? They're variable size data vectors. They're unevenly sampled. They have different sampling at different wavelengths. And they have phase gaps that can last even months over the lifetime of an object. There is a couple of years. There are multiple relevant timescales in the physics that we're interested in. And of course, there are aleatory and epistemic heteroscedastic uncertainties. So it's kind of like a pessimally posed problem for AI, or really any analysis. And so in my title, Do Androids Dream of Exploding Stars? I think it's more likely androids have nightmares about exploding stars. Okay. This is the result of one of the winner of that challenge. This is a confusion matrix, so anything on the diagonal is great, anything off the diagonal is a misclassification, and I think it's a really impressive result given the setup that I described. One thing that I forgot to mention, severe class imbalance, that is also not the same in the training and in the test set. Good luck with that. Let me briefly make a point. While we have trained a number of AI, meaning neural network and generally machine learning models at doing this, we have trained it largely on simulated data. There is very much a risk for our community here. Some of that data is really not characteristic. And we are finding these things as we continue to evolve our understanding of objects. My former postdoc, Sumaya Habkash, wrote a paper on supernova, on stripped envelope supernova, like a subclass of supernova. and their diversity, and found that they were not represented correctly in the original data set. And so the state-of-the-art sort of in the field has become using Gaussian processes to interpolate between observations and also get uncertainties from these observations. This is the same paper that I showed you the confusion matrix from before, and the winner of that challenge. There's other work that use the same paradigm. In particular, I'm gonna give a shout out to this really interesting work where, in order to feed this really bad behaved non-tensor to a neural network, this is pre-transformers, so it's a convolutional neural network, Helen to turn the data and their uncertainties into heat maps, two-dimensional heat maps, so that we could use methods based on imaging to images to process these the LSST data, and with really good success. Fine, more that I could say, but that's principally very disturbing, because the way an image model works is you're taking 3 color channels of the same object, and there's correlation in the emission, and that correlation gets, you know, the CNN feature map get averaged after the first layer. Now we're averaging between what gets extracted by the image and what gets extracted by the uncertainty. So it works, just like a lot of things in neural network, because remember the scaling law, it really works. But methodologically, it really is creepy that it works. There are methods that are much more correct at dealing with this, but they don't really, in some cases, they don't have the same success. In most cases, they're really hard to train. They require much more data. One possible solution, well, there's 2 possible solutions to this problem. One is perhaps we need to abandon Gaussian processes, because the way in which Gaussian processes work is by imposing a kernel from your expectation that you understand what the covariance in the data is, what the evolution and covariance in the wavelength space is. But typically, we apply this kernel to a diversity of objects that work principally differently. And there may be unknown objects in there, which we really want to discover. And so Gaussian processes, I think, while it's working, is a quite risky proposition. There is an alternative to Gaussian processes, which is neural processing, and one of my students, Siddharth Chaini, is working on it, where in the fewest words that I can express this, you're kind of replacing the kernel itself with a learned neural network, with the learned parameters of a neural network. And this is emerging in astrophysics as a fairly novel technique and very interesting to keep an eye on. And of course, the other solution is transformers. I thought I had a slide on a transformer project, but I don't. It's transformers because they allow more flexibility in by associating timestamps to the data points. How much time do I have? 7. So do I finish at 5 minutes? Okay. Okay. So I'm gonna finish with not this. I'm going to finish with this because it's my brand new NSF grant and also a NASA Finance Fellowship awarded for this idea on anomaly detection. I think anomaly detection is really the most exciting problem that LSST the most exciting opportunity for LSST. Can we discover new physics? How do we prepare to discover new physics? That's a really super interesting question. And of course, we all want to be Insta famous, and if I discover new physics, I can pretty much be sure that I will be. Let me take you to this related work by my student Siddharth Chaini, who's a NASA Finance Fellow. He developed recently a classifier for transients. This is not anomaly detection yet. It's just a classifier for transients that cleverly uses, instead of using just the Euclidean distance between objects, in whichever representation space you take your object, so whatever features you extract from your object, those features can be extracted, for example, by a neural network. Instead of just using the Euclidean distance, which is what we normally do to see where object set and then aggregate them. He uses an ensemble method and uses 16 images, 16 distances at once. This is effectively the same as pre-processing your feature space 16 different ways before you run your model. And this paper is out and the classifier works, yay. But we were interested in how would this classifier perform on anomaly detection. And we found out something that is really interesting, I think. This is not that classifier. This is an isolation forest, one of the most commonly applied methods for anomaly detection. The way we set up the experiment, we gave the models known classes, Cepheids, R, Lyrae, a couple of variables that I don't remember. And then we injected the data with classes that were not in the learned set. We injected it with supernovae. We injected it with Myra, all weird things that should be weird for the model because it has never seen them. And we found that isolation forest and a bunch of other methods, bunch of other methods. Is there an actual microphone? Tend to find the in-set anomalies much more easily than the out-of-set ones. So when we run the isolation forest, and I'll show you different methods, what we found was that the emerging anomalies were the weird Cepheids, the class that we had trained on. Whereas our model was pulling out one after the other, all the things that it had not been trained on. So I think we need to really be careful about and ask ourselves the question, are we prepared to discover new physics, not only to discover weird things in our data? The way Sid is presenting it is, if you think about having a follow-up budget, what fraction of the objects that you follow up based on how the anomaly detection method scores them is an actual new, novel, truly unknown thing. And his models are at the top, depending on some hyperparameter choices. There's a couple of versions of the model. And you see here all the other models. The isolation forest is this line. And actually, autoencoder-based methods in the literature that are neural network-based and expect to perform really well actually have the highest tendency of finding inlier anomalies rather than out-of-sample anomalies. And that's surprising and exciting, and we have submitted this for the new RIPS workshop. Okay, so I'm gonna finish with a couple of minutes of lecturing on other topics. So let me ask first, who in the room hates penguins? Does anybody in this room aspire to murder penguins? I'm going to argue that we all are guilty of possibly murdering penguins because AI isn't free and the neural networks that we train do cost true and effective resources that are contributing to climate change, ecological racism, and a variety of other things that you probably don't want to be responsible for. So use AI responsibly. One recommendation that I have is let's start really seriously measuring the impact of our models, which is not easy because you start with like a collab notebook and you don't have in mind that you should start keeping track of how many times you train that before you deploy your final method. But I would encourage the SkAI leadership to seriously think about tracking CO production of our projects and set the example for being aware of this and reporting it. You can track it with this handy tool, and then you can go to the EPA webpage where it can tell you how many trees you need to go out and plant to offset the carbon footprint of your AI models. Shout out to the EPA. This is a fun story if you haven't seen it. Apparently the fact that we are so polite to ChatGPT and all the other large language model has a massive environmental footprint. Like, that's the equivalent of 122 Olympic-sized swimming pools being built. That's the CO2 footprint of people thanking ChatGPT. Foundation models offer an opportunity, I think, for us to be more responsible users of AI. I have a bunch of slides that I never get to show because I always get to this point of the talk late about what foundation models are and how they work. But they rely on the idea that our models learn very generalizable things about the data in the early part of the model and specialize on a task in the late part of the model. So you can take a very large model that costed a lot in resources to train and keep all the layers up until the very last few ones as a general purpose machine, especially if you're training in specific ways, like with contrastive learning, and then retrain the head to do the task that you want. If we embrace this as a method for astrophysics discovery, this might really be transformational in the carbon footprint that we have. However, I'm worried about a trend that I'm seeing of a bunch of people building relatively small foundation model and pushing them in the literature, because that's just the opposite. That just goes the other way. Then we all train extremely large models, and we're the only one who use them. So please be aware of this trend and try to fight it. And then I'm going to leave you with some quotes. Knowledge is power. Astrophysics data is a sandbox. It has no social value, no privacy risk. We can safely learn about bias building into algorithms and how to correct it. As I give you my talking points, I also show you recommendations for very important ethics of AI literature that I hope you consider reading, starting with Unmasking by Joy Volamini. Data feminism brings us to ethics of AI is a critical element of the education of a technologist. So if you're in a position of power in terms of being able to direct the curriculum, please try to ensure that our astrophysicists are trained not only in AI deployment and the development of models, but in AI ethics, because they are very likely to end up working for an insurance company where they can do some serious damage if they don't have that training. And AI is a transferable skill, and you yourself can choose to use it for good. My last quote is by Ruha Benjamin. She is a scholar of technology at the intersection with race from Princeton. She wrote this beautiful book, Race After Technology, and she uses the word astopia, a word I'm borrowing from Margaret Atwood to describe the fact that the future is us. However loathsome or loving we are, so we will be. Whereas utopias are the stuff of dreams, and dystopias, which we often hear referring to about AI, are the stuff of nightmares. Utopias are what we create together when we are wide awake. I'm gonna stop here. I don't know where my last slide is.
And if you do have a question, please raise your hand and wait for a mic to come to you so Zoom can hear you as well. Questions from the audience?
Because you told them that I talked and I can keep them up.
Also, I guess I will take chair's prerogative and ask you a little bit more. You've been not controversial, I'd say, about the ecological impact of these AI models, but the footprint here that we're having in astrophysics is tiny compared to, of course, any of the industrial applications of AI. How does one put a relative value on what we're doing versus what industry is doing in sort of the bigger picture of value of these big models and how that has an ecological impact?
Only that as a question. So yes, it's true. The environmental footprint of astrophysics AI model is tiny compared to the environmental footprint of all the models that are deployed in the real world. But I want to say two things. First of all, we have the power that we have and we influence the areas where we are. And the fact that those are not inherently changing the world shouldn't stop us from taking direct action over the things that we have power and responsibility of. Second, it could build momentum if we spearhead a culture of responsible AI usage that can leak out of astrophysics into other areas of academia, and that can leak out into the real world. And also, third, like I said, we train astrophysicists but a lot of them end up working for Google, end up working for different companies, startups, where they control an entire different area and they can have influence over an entire different sector.
Glass?
Yeah, thank you for your talk. The work on anomaly detection, the thing you sketched there where you model the normal part and then you compare it with what you observe to find the abnormality and so on, is something that has been used in different fields like medicine, fMRI data, or internet data and so on. So I'm wondering if in your work, there's something kind of special that has to do with you used Rubin data, right?
Yeah, no, so we use both simulated Rubin data and ZTF data.
Right.
So I think that no, there's nothing special. And I've advocated that when we have like anomaly detection groups and discussions, for example, the science collaborations have about a couple of anomaly detection task forces. I've advocated fiercely there that we need to connect to all the other areas because there are anomaly detection methods that we're blind to just because they're applied to other things. And there's an opportunity that is specific for us in Rubin. There's a problem of data encoding that is significant. And there's a problem of data imbalance that is really going to impact our ability to find new physics in the midst of such abundance of classes that we know to different degrees. And I think those are specific. I don't know that they're unique, though.
What's the encoding problem you're referring to?
The fact that if we are talking about likers, they're really sparse. And so the way in which we extract features from them or encode them to pass them to a model is very difficult due to the sparsity in both dimensions.
Okay, thank you.
The very sort of limited information content of our data compared to.
I see another question in the back there. I'll take Rachel's question and then I think we should let Fed go.
Because I got to go teach.
Yes, exactly.
Okay, well, I'll try to be fast then, Fed. As context for everyone else, I'm one of the people on the survey cadence optimization committee that Fed mentioned potentially replacing with AI. So that's sort of the
long-term goal.
So this is something that I've thought about pretty seriously and wondered about. And one of the things I've wondered about when we try to find places where AI can contribute is, how much is a particular problem relying on somebody finding, creative solutions that are outside of the space of what's been previously considered, and is that a problem? And I felt like in this particular context, sometimes we've gotten really creative solutions that are kind of outside the box, or someone's new creative survey strategy idea caused a problem we hadn't had to think about before, and so we had new problems to bring in. I'm curious if you like how you relate to that when you're thinking about these different areas and applications of AI.
Yeah, so I want to say that I actually don't think that replacing the committee with an AI is possible at the moment or on the short term for another problem, which is that the committee is also soliciting the axis along which we measure success. That I don't think can be replaced by an AI because it requires human contact with actually human, like physical, biological beings that study scientific areas. So I think that's the most difficult problem. I think the other ones are solvable algorithmically though, right? So if I give an AI the opportunity to arrange 10 years of observations in any which way, so long as I know what the axis along which to measure success is, then that can be really creative. That could come up with like a rolling cadence, sorry for the inside reference, a rolling cadence of its own, right? But the problem is that I don't know that I'm measuring the things by which I would know that there is a problem. So I think it's more about like dimensions of the problem than about algorithm to solve it.
So I see there are more hands, but I know that Fed has to teach her class in 20 minutes. So let's thank her again for this opening plenary.